Hello and welcome to Lesson 3 of the GPS course called The Framework. In this lesson we'll talk about the context in which GPS exists, where it came from, and how it operates today within the context of the other systems. In the early 1970s, the Department of Defense looked around to see how many different kinds of positioning systems it currently had available, and there were more than 120. They were of various kinds. Some were terrestrial, some relied on electromagnetic signals, some were optical. There were various kinds of positioning systems in place. A plan was made to combine the systems, to integrate them and to collect them into one as much as possible. And this is a look at some of the technological forerunners to GPS. In general, the idea always was to take from the previous systems the aspects that worked the best and to leave behind those that left something to be desired. And it was from this experience that Navstar GPS developed. As I mentioned, many of the systems were terrestrial. And of course radar, one of those, radio detecting and ranging, was built in World War II and became a very powerful tool in the hands of the Allies in winning that war. Now, radar, of course, operates in part of the electromagnetic spectrum, and the L-band, which, of course, we currently use in GPS, is really part of a identification system that was originally instituted in World War II. L-band was designated L because the wavelength was long compared to others. Here is a chart of the electromagnetic spectrum, a portion of it. And as you see, visible light is a very small range in the middle. And microwaves, which is the area where the radar bands live, is considerably outside the visible range. Now the L band, as it indicated here, is 15 to 30 centimeters. The S band, S for short, 8 to 15. Actually there was a much shorter called the Kurz or K band that the Germans were using. Then there was those that were designated C-band and many others. But when we say L-band, we're referring to this identification system. And of course, with the wavelengths of the GPS carriers in the neighborhood of 20 centimeters, they fit well within that context. But overall, the idea of radar measuring distances with electromagnetic signals was instituted with that technology. And of course we're still making the most of it. So one idea that originated as far back as that era is this fundamental concept of being able to use electromagnetic or energy to measure distances. And of course, since the concept of measuring distances with electromagnetic energy was introduced, it wasn't long before it was used in surveying. In the late 40s and early 50s, Canadians were using SHORAN, which is a type of terrestrial positioning based on towers, as you see here, to achieve precisions as high as 1 part in 56,000 on lines of several hundred kilometers. Now, of course, this was extraordinary in those times, to be able to measure distances of this magnitude. And as it says here, in the early 50s, the Aleutian Islands off the coast of Alaska were measured by SHORAN. And in the 50s, the United States Air Force did trilateration between Florida and Puerto Rico, and then continued to Trinidad and South America. And of course, trilateration is a familiar term that has come up again in GPS, positioning based upon distances. Now, it's worthwhile to note that SHORAN and its other brothers at LORAN and Hiran are still terrestrial based, even though, of course, they're using the electromagnetic signals. Now, Hiran Surveying was really the first intercontinental system. As you can see in this graphic, it was used to connect datums across the oceans, and this is a remarkable achievement, something that had really never been done before, and especially remarkable given, again, the fact that this is a terrestrial system. But keep in mind that these datums, for example, the European datum being connected to the North American datum, was something that really had not been accomplished before. And up until we started thinking in these terms, there was really no reason, I suppose, to consider that any kind of a worldwide foundation of measurement was practical or needed. Now, of course, today we have a tendency to think of the Earth as a whole planet, and we want the measurements to be consistent around the entire planet. But before intercontinental connections were made, this really wasn't necessary or taken seriously. So one of the forerunners of GPS is simply the mindset of thinking of the datum being a Earth-centered and Earth-fixed system. Well, Sputnik changed the idea of a terrestrial surveying system or measurement system. Now, of course, this simple satellite didn't really by itself do anything except send a pulse that was identifiable by any shortwave enthusiast around the world. But it also accomplished a great moment of awakening concerning the orbiting of artificial satellites. And it was, of course, obvious that to have a platform that was that high, with, again, electromagnetic signals emanating, would be able to cover the entire planet much more effectively than any terrestrial system, even Hiran, could manage. But there were other aspects of the Sputnik signal that might not be so immediately obvious, that in fact we're still using today in GPS. One of those is the more flexible frequencies that can be used. One of the things that allows a terrestrial system to be able to cover a very large area is the propagation of the radiation near the ground. You've undoubtedly heard of the bouncing of radio waves off the ionosphere, for example. Well, the spherical shape of the Earth favors low frequencies that stay close to the surface. A LORAN-C, a long-range navigation C, can be used, as it says here, to determine positions up to 300 kilometers from a fixed transmitter. But the frequency has to be rather low for this to function. But also the idea of these low frequency systems really was done to do positioning that didn't have to be to the level of accuracy that we're dealing with GPS. Earth orbiting satellites, on the other hand, allow the use of high frequencies, and they can, of course, cover the entire planet. Of course, launching such transmitters and obviously frequency standards, oscillators, into orbit, that was a pretty tall order in 1957 when Sputnik went up. Some, as it says here, some of the earliest extraterrestrial positioning was actually done with optical systems. Here's a neat picture of a track of a satellite against the so-called fixed stars. Of course, it is possible to determine the position of a satellite in this way, because the stars have known coordinates in the right ascension and declination system. And so if one knows the time and knows the stars in the background, it is quite possible to learn the ephemeris, or the position of the satellite, based upon that control. And this is an extension of astronomy that has been used, and to some extent continues to be used, in terms of positioning the satellites. For example, it's worth noting that some of the major remote sensing satellites have star trackers on board that help determine their orientation and position. Of course, by implication, if one knows the position of a satellite relative to a sensor on the Earth's surface, then obviously it's possible to extrapolate the position of the sensor on the Earth's surface. And here is one of those kind of sensors, a ballistic camera. These cameras have very fast chopping shutters that can track rapidly moving satellites or other bodies, and then from that determine their position by triangulation. And so this is a positioning system that uses extraterrestrial objects to determine the position on the Earth's surface. And as it says here, the accuracy of such networks has been estimated as high as plus or minus 5 meters. Now, of course, we think of GPS as being much better than that, but again, the idea of using satellites to get positions on the Earth has a history of many decades. We discussed EDMs earlier, and it's possible to use EDMs as an optical system to determine distances. Satellite laser ranging, SLR, can measure distances using an electronic distance measuring device, an EDM, using a laser that points from the Earth to the satellite, and of course obviously the reflectors on the satellite then can return that signal to the terrestrial sensor. This way of doing it is obviously what we've discussed earlier in terms of phase comparison with a reference wave at the EDM, and works very well for satellites orbiting. As a matter of fact, the GPS space vehicles 36 and 37 have retroreflectors or corner cubes on board for this purpose. And some of the newer satellites probably will continue that trend. Also, this system is used for lunar laser ranging. There are banks of reflecting retro prisms on the lunar surface that were left by the manned missions, both Russian and American. And we can now determine the position of the moon relative to the Earth using electronic distance measuring to centimeter precision. This, of course, is extremely useful for many positioning needs. Of course, obviously, this sort of measurement requires two-way communication. And obviously, it requires the sending of a signal from the position where the unknown object is. In other words, this observatory on the Earth's surface can determine its position by using laser ranging to satellites, but it must broadcast to be able to do that. And as you remember, GPS is different in that it's a passive system. It does not broadcast. Obviously, one of the drawbacks to optical systems is they can be restricted by clouds and other atmospheric troubles, fog, and so on. Clear skies are hard to come by sometimes, and of course turbulence can also be a problem, and as we know, the troposphere and the ionosphere can be very uncooperative in that regard. Clearly, also, since it's necessary that the place where you want to derive your position must be able to broadcast a signal, you have to have expensive and sometimes bulky equipment. So there are some drawbacks to the optical idea. And of course, one of the difficulties of these two-way systems from the Defense Department's point of view was that the position needed to be revealed by this broadcast that the system required. The two-way systems require the revelation of the sensor that is trying to find its position. This is not secure, and the passive approach was considered to be much better. One of the first systems to actually make this successfully work was Prime Minitrack, and it relied on phase difference measurements of a single frequency carrier broadcast by satellites and received by two ground-based antennas using interferometry. Now, interferometry, interestingly enough, was actually used in the very first working GPS receiver called the micrometer. It's the measurement in the difference between phases of signals that originate at a common source, but travel different paths to the receivers. Of course, if a signal travels different paths to get to the receiver, it arrives out of phase, out of step with each other. And it's the analysis of this phase difference that allows one to determine extremely accurate ranges. And one of the great advantages of this approach is that it allows the receiver to be passive. Here's an example of interferometry, very long baseline interferometry, or VLBI. Actually, it originated in radio astronomy using a quasar, which is, of course, a very consistent radio source in the sky, and tracking these quasars from radio telescopes that can be on different continents. They can be extraordinary distances determined very accurately using interferometry. And as a matter of fact, such a VLBI, or very long baseline interferometry, is used today in the network of control points on the Earth that are used for monitoring tectonic movements, and also the foundation for the International Terrestrial Reference Frame, which we will talk about later. That can be used to control GPS surveying's very accurate positions. So VLBI still has a real role to play in GPS. It was used, as it says here, as early as 1967, and like SLR, it proved valuable information about the Earth's gravitational field and rotational axis. Now, this is important to mention because, of course, now that it became possible through satellite means to combine the datums of different continents, the shape of the Earth and the orientation of the Earth, and determining those things quite accurately became essential to the use of satellites. Satellites orbit, of course, around the center of mass of the Earth, and the shape and the character of the planet is something that needs to be determined to be able to make the most of extraterrestrial positioning. Now, one of the first systems, again a passive system, to actually in a practical way use satellite tracking to determine positions on the Earth's surface was called Transit, also known as the Navy Navigational Satellite System, or NNSS. Now, one of the things that was learned by tracking Sputnik in 1957 was that the Doppler shift of the little beep, beep, beep that a Sputnik generated was enough to determine the exact moment that the satellite achieved the closest approach to the Earth. Now, this idea led to the creation of NNSS, or the Transit System, that was then used by the Navy, particularly for aircraft and ship navigation. It was declassified in 1967 and used up until it was switched off at the end of December 1996. Now, of course, the idea of the Doppler shift, as illustrated here, is that as an observer notes a constant signal approaching, the wave fronts are smashed to closer together, and as that signal source moves away, the waves are pulled further apart. This is often illustrated by the change in pitch of a railroad horn. As it approaches, it seems to rise, and as it moves away, the pitch seems to fall. And of course, the same effect is obvious with a satellite signal. As the satellite approaches the observer, wave fronts are pushed together, and as it moves away, they're pulled further apart. The rate at which these happen can be analyzed to determine the position of the observer in a passive way. Now, Transit made the most of this and used the Doppler signal to be able to determine positions on the Earth. It had some difficulties. There were only 6 satellites in the constellation, and therefore an observer had to wait quite a long time often to receive the satellite signals, up to 90 minutes. And at least 2 passes were necessary for reasonable accuracy. Also, the orbits were rather low, 1,100 kilometers, and therefore atmospheric drag and variations in gravity and etc. made the satellites less stable than they might have been otherwise. But it's instructive. As I said, both the advantages and the disadvantages of the transit system and these others that I've talked about contributed to the design and gave the design of GPS more chances for success by building on the experiences of these previous systems. Now, some of the systems that were developed with transit were rolled into GPS. For example, the fact that there are 3 segments, the control segment, the space segment, and the user segment, and we use that with GPS. The fact that there were 2 frequencies. Now, they were quite different with transit, but GPS, of course, 2 carriers. Same idea. And in fact, GPS does use the Doppler effect as one of the observables. So there are some similarities between the two systems. And obviously the transit system was able to link international datums, being a very high platform and satellite-based. Submeter work was possible with the transit system, although long occupations were required to achieve that, up to a day. But in early 1973, GPS was starting to be considered. And perhaps one of the reasons that the 20,000 kilometer orbit was chosen was learning from transit. It became apparent that a higher orbit was better. Also, the rubidium and cesium oscillators on GPS were obviously a big improvement over the quartz crystal oscillators used in the transit satellites. So again, the GPS system built on the shoulders of the systems that came before it. Now let's talk about some of the standards that were stipulated for NAVSTAR by the Department of Defense. Some of the wish list that guided the design. Now here up at the top we have these diagrams of the signals, the L1 signal, that carrier on the left, and the L2 signal on the right. Obviously at the L1 signal, as you know, both the CA and the P code are on that carrier, and on the L2 just the P code. Well, the genesis of GPS, of course, was the Defense Department. It was in the Defense Department. And in 1973, the Joint Program Office was given the directive to establish the GPS system. Now, one of the things that was necessary was that it be secure and passive and global. A pretty tall order all by itself. Secure and passive sort of go together in that the user did not have to reveal their position when they use the system. So obviously broadcasting a signal was out of the question. Also, as you see in these diagrams, it was necessary that the signal be resistant to jamming. And so therefore the GPS carriers are spread spectrum, meaning that they occupy more width, if you will, more bandwidth than they minimally would need. This makes them more secure to jamming and spoofing. Obviously, too, they wanted to prevent either intentional or unintentional interference. And the signal had to have a large capacity. As we've already discussed, a great deal of information has to come down on this GPS signal, since it is a passive system, to the receiver to allow positioning to be successful. And as we've discussed, it was necessary and is necessary for there to be at least 4 satellites above an observer's horizon to achieve a successful position. Unlike a transit of 1 satellite at a time, GPS requires the solution of X, Y, Z in time based on a minimum of 4 satellites. So therefore, it's necessary to have a constellation that allows that to happen 24 hours a day, 7 days a week, in all parts of the globe. Pretty tall order. As I mentioned earlier, the GPS signal is a spread spectrum signal. All weather performance is necessary. It needs to be able to be corrected for ionospheric delay. So therefore, a dual frequency transmission is needed. And of course, this is similar to the transit system. A high frequency is required, as we've discussed earlier, and the GPS signal needs to be secure from jamming and multipath and interference. That means that we're talking about a spread spectrum signal, a bandwidth that's wider than is needed. And this wide band allows for this pseudo-random noise code that we've discussed to be impressed onto it. The objective, of course, was to build the perfect system, and whether or not that's been achieved, there are several of the specifications that have been met rather well with GPS. It's a passive system. There's no need to broadcast any signals. It can be denied. It can be turned off when the Department of Defense so desires, any portions of it. It's resistant to countermeasures, meaning spoofing, for example, is a term used to indicate the idea that a bad guy could broadcast a signal that appears to be a GPS signal to try to confuse the receivers. Well, with the pseudo-random noise code being such a complex code, it is rather difficult to mimic. It works in real time. In other words, as it has developed, it's quite possible to get GPS positions in real time. It should be applicable to joint and combined operations, militarily speaking, and it should be able to work on common grids or map datums that are appropriate for all users. This is very true. One of the things that GPS is very good at is taking its native format in Earth-centered, Earth-fixed XYZ coordinates and transforming them using the microprocessor and the receiver to virtually any well-defined coordinate system. The positional accuracy should not be degraded by changes in altitude nor by the time of the year, time of day or year. Yes, GPS works well at the top of the mountain and down in the valley, well, except for multipath to some degree. And operating personnel should be capable of maintaining the system. It should not be dependent on externally generated signals. Of course, that's true. The signals come directly from the satellites. It should not have decreasing accuracy over time and distance traveled. GPS has been extraordinarily effective on measuring very long baselines. It's all a pretty tall order, but GPS has lived up to most of it. Actually, the civilian portion of GPS was not really a focus in the beginning of the system. It was decidedly a Defense Department system, but the concept was that if civilians were to use it, that 100 meters horizontally and 156 meters vertically at 95% reliability was the goal. This was the Standard Positioning Service, or SPS. However, it became apparent early on that civilian receivers were doing much better than 100 meters, and so therefore selective availability was instituted. This was based upon a dithering of the clocks in the GPS satellite. And obviously, as you know, if the clocks in the satellite or the oscillators in the satellites are tweaked, are moved, and don't keep a steady standard, then the positioning derived from them would suffer. And so using selective availability for quite a long period of time in the instituting of GPS, it was possible to degrade intentionally the accuracy available to the civilian CA code users to the 100-meter specification. Well, fortunately, selective availability was switched off May 2nd, 2000, and so that is no longer a consideration. I must mention that since surveyors traditionally worked with the carrier phase observable to achieve high accuracy, the dithering of the pseudo-range codes didn't affect surveying positioning. However, for those who use pseudo-range or code phase receivers primarily, selective availability was a problem. And since it has been switched off, of course, the accuracy of those sorts of receivers has improved markedly. Now, here's an old friend for me. This was the first functioning GPS receiver, the macrometer. As I mentioned, it was an interferometric receiver. You see here the receiver itself on the floor next to the tripod. It was rather heavy. It took two people to carry it, actually, and we carried them in vans, specially built for the purpose. The macrometer had to be, of course, used simultaneously with others. The same concept as we discussed of relative positioning, receivers operating simultaneously. And they had to be brought together, and their clocks had to be synced up. Their oscillators had to be synced up because, of course, they didn't have access to we didn't have access to the navigation message since we weren't using the codes. It was a completely codeless receiver. The antenna here was a meter square of aluminum, and you can see the dome with the dipole antenna on the underneath part. And of course, the antenna was cabled to the receiver. You can almost see the tape drives on the front. We used tapes to record the observations. And the system ran, as I recall, on 110 volts, so we had to carry generators with us. It was quite a beefy system to carry around and quite expensive. But it worked, and it worked rather well. It was possible to achieve 1 to 2 parts per million of the station separation, which was much more accurate than the 100-meter spec we were talking about earlier. And of course, this was possible because of the use of the carrier phase or the carrier beat phase observable. And so it was extraordinary accuracy from the very beginning, from the very first GPS receiver. Continuing on with the civilian point of view, which of course is our primary focus, today, with a mask angle of 10 degrees, it's possible to have up to 10 satellites above the horizon. Of course, when we first started, we were very happy when we were able to have 4. So it's obvious that as time goes on, GPS has resulted in the cost of the receivers going down and their sophistication going up. And GPS clearly has been replacing its predecessors. Now, the extraordinary range of GPS, and it's really a remarkable story of how rapidly the system has realized its potential. First, let's look again at the space segment, which of course are the satellites themselves. A full constellation is 24 satellites, and that's basically what we have, plus some orbital spares. And one of the reasons we have the orbital spares is to be sure that if satellites wear out or become out of service, there is already a satellite available to take the place of any that go down. Now, there are 6 orbital planes, each one inclined to the equator by 55 degrees. The constellation is symmetrical and uniform. Orbits are posigrade, meaning that it moves in the same direction as the Earth's rotation, and the orbital period is 12 sidereal hours. which is, of course, different from solar time, different from UTC and the normal time on which we operate. Now, one of the things that's been very good about the GPS system is that the satellites have tended to outlive their design life. They have done very well in being lasting longer than they're generally thought they would. This is sort of a mixed blessing, which we'll talk about in a little bit. Now, the 4-minute difference that's mentioned here on this slide refers to the fact that since the orbits are measured in sidereal or star time, that's different than solar time, that actually a satellite would find its way back to exactly the same position that it was in the sky the previous day, but it would be 3 minutes and 56 seconds earlier, or 4 minutes earlier on the solar time scale. So if one was measuring a particular constellation and wanted to return back to the same constellation on the next day, it's good to be there 3 minutes and 56 seconds earlier to see the same constellation. This, of course, is the difference, because of the difference between solar and sidereal time. Now, the constellation that exists satisfies many of the design characteristics that were required by the Department of Defense. It covers the entire Earth with the fewest number of satellites, and because the orbits are so high, at 20,000 kilometers, the effects of gravitational and atmospheric drag are minimized. The discussion of dilution of precision, or DOP as it's known, is appropriate to this portion on the space segment. Put simply, a high value for the dilution of precision is bad, and a low value is good. A high value happens when the satellites, the control points, are crowded into one part of the sky. As you can see, the geometry of the ranges when this occurs is not good. The intersection is ambiguous. So the dilution of precision value would be high in this circumstance. It's sometimes called PDOP, or position dilution of precision. Now, good DOP, where the value is low, occurs when the satellites are much more spread out and embrace a larger portion of the sky. Now, there's various flavors of it. There's HDOP, horizontal dilution of precision, and VDOP, vertical dilution of precision, and so on. PDOP is perhaps the most common, which combines both horizontal and vertical. But the idea is very straightforward in the sense that the better the geometry, the better the intersection of the ranges from the satellites, the lower that the dilution of precision value will be, and the better the position derived will be. This is, as I say, a very practical consideration in GPS work. Now, as you see in this slide, the mask angle that I've mentioned plays a part here. Clearly, if one had 4 satellites and 3 of them were at the horizon and one was directly overhead, this would be a very low dilution of precision value. However, one wouldn't want to track satellites that were right against the horizon. One wants them above this mask angle, a 10 or 15 degree mask angle, to try to minimize the effect of the ionosphere. Now, when high DOP values do occur, they can reach a level that is actually an outage. In other words, it's not useful to observe GPS when the satellites are crowded together. Now, normally people have become very acclimated to the concept that GPS is a 24-hour, 7-day-a-week system, and the idea that one can simply turn on a GPS receiver and start working under all circumstances. has held sway. Of course, that is not wise. The position of the satellites in the sky is critical to good positioning. Here we have a polar plot, as it's called. In other words, this concept would be as if one were looking straight up, and the satellites, as they would cross that point of view. Now, where the satellites are during the window of observation does affect the quality of the outcome. Here's an example of this idea. As you see in this slide, the number of satellites is in the graph at the upper part of the view. And the PDOP, or position dilution of precision, is in the lower part. Now, clearly, the spikes, spike 1, 2, 3, and 4, are areas of very large PDOP. And this means, of course, that during these moments, the positions that are collected are very suspect. Now, it appears that, for example, starting at 0 hour, that the satellites vary between 7 and 8, and then suddenly, at about 2, some of them begin to set. And it drops down to constellation above the horizon, drops down to 4 satellites. Well, when that happens, clearly they have been crowded into one part of the sky, the 4 that remain after the others have set. And at that moment, there's a rather extraordinary spike in the PDOP. Well, obviously, one wouldn't want to be observing at that time. Now, then, shortly thereafter, some of the satellites return. And it goes back to 8 and 9 satellites. During that period, the PDOP is very low. It's below 4, and a good time to observe. However, even when there appear to be many satellites above the observer's horizon, yet there's another spike, number 2, and spike number 3, and of course, one could say, why, if there are so many satellites? Well, satellites are, of course, always moving relative to each other, and even though there are many, they can be, again, crowded together, and the PDOP can be high. Well, going past about 12 hour and moving on, the circumstances are very good. There's many satellites, the constellation is healthy above the horizon, and the PDOP is very low. But just before between 18 and 20 hours, we reduce down again to 4 satellites, and then again the spike in the PDOP occurs. So, as you see, it's not really as straightforward that any time at all times the PDOP will be low and this constellation will be good. Well, nor is it correct to say that simply because the constellation is good, the PDOP is low. One has to look at it in some detail, and it's valuable to note that most processing software packages do allow you easily to make graphs of this type if you have a current ephemeris in your system. And it's lucky that those current ephemerides can be downloaded from the internet, as well as collected from the satellites. Now, continuing our discussion of the space segment, here is the Block 1 satellite. These were the first launched. The first one went up in 1978. There are none of them functional today, but they certainly did an extraordinary job in getting the system started. And one could say it was an experimental system at that time, but it certainly has worked out well. Now, the Block 1 satellites started a trend that continues to this day. As you see, the design life of these satellites was 4.5 years, but their actual average lifetime turned out to be more than that, 8.76 years, nearly twice the design life. that is something that continues. As I say, the GPS satellites have mostly outlived their design life by quite a bit. Now, the Block 2 satellites, as indicated on the cover page of these lessons, are really the workhorses of the constellation today. They're 28 built, and the first left Cape Canaveral on February 14th, 1989. It's almost twice as heavy as the first satellites, the Block 1s, and has a design life of 7.5 years. Now, the mean mission duration of 6 years is a similar number. The Block 2Rs are for replenishment. Are like Block 2 satellites. They have some good enhancements. They have autonomous navigation capability due to their inter-satellite linkage, meaning that these satellites actually have GPS receivers on board. And of course, there's no reason why that can't work. They are GPS satellites with GPS receivers. And these receivers allow them to know their position rather well within the constellation and to self-navigate. A good idea, I think. Now, the Block 2Fs are the follow-on satellites. These are rather sophisticated from the Block 2s comparatively. They will have a third civilian frequency. They'll have the L2C signal and also eventually the L5. This is the new carrier frequency. This will be very helpful because, as you know, the ionosphere modeling is an important part of error management in GPS. We can model it to some good degree with 2 carriers. 3 will obviously make that modeling even better. Now, we've already talked about the turning off of the selective availability, but anti-spoofing, which is a different component of security in the GPS system, continues. Anti-spoofing is the encryption of the P code into what is known as the Y code. And this, of course, is this encryption is to make it difficult to impossible for bogus signal to mimic the GPS code, especially the secure GPS code, well enough to fool a GPS receiver. And this is known as anti-spoofing. One of the best and most important numbers here in this slide is the fact that the GPS satellites move at a speed of about 8,700 miles per hour. That, of course, is an extraordinary rate, and this again underlines the importance of the solution of time in the positioning using GPS. Also, it's interesting to note that the satellites pass through the shadow of the Earth from time to time and have onboard batteries to provide power when the solar panels are in the shadow. Now, moving on to the control segment again. Remember that the control segment is a combination of monitoring stations and upload stations that allow the navigation message to be updated. And the control segment is all fed into the master control station, which is now at the Schriever Air Force Base in Colorado Springs. The monitor stations track the navigation signals of all the satellites. They provide meteorological, pseudorange, and carrier phase data to the master control station. where all of this is smoothed using Kalman filtering. We'll talk a little bit about that. The carrier phase measurements are used to smooth the pseudo-range data to reduce the measurement's noise. The information is then processed at the MCS and used to update the satellite's navigation message. The MCS sends updated information, including the broadcast ephemeris and satellite clock, to the satellites through ground antennas at uploading stations. So the data goes in, it's processed, it comes back out, and then is uploaded back to the satellites. On this slide, we have a nice image of the tracking station on Hawaii. Now, I mentioned Kalman filtering. It was named for Ari Kalman. It's really a least squares statistical method for condensing and smoothing large amounts of data. And I like to use the example of an old-fashioned car speedometer. If you ever had an old car that operated on the spinning cable inside a housing, you know that those had a tendency to wear out, and the cable would cause the needle on the speedometer fluctuate, let's say between 56 and 60 miles per hour. And the driver could estimate that, given that bouncing needle, that the true speed was somewhere around 58. And then illustrate adaptive gain by stepping on the gas and noticing that even though it still continued to bounce, it would actually move up as the speed of the vehicle increased. This is a good analogy, I think, of how Kalman filtering works, and the concept is that when there's a very large amount of data, this strategy, this recursive solution, can be used to prevent the overwhelming of the processors by this blizzard of data. Kalman filtering is used really throughout GPS technology to make the most of the data that is received. Now, it's valuable to know that the control segment means that every GPS satellite is tracked by at least one of the monitoring stations, and now that we have an upgraded control segment, most of them are monitored by at least two simultaneously. This is a very good thing. Now, while the Block 2 satellites can function without new uploads for 14 days and the Block 2A satellites for 180 days, we really wouldn't want them to do so because, of course, the navigation message would deteriorate rather dramatically in those kinds of periods. So one of the things I wanted to mention at this stage is the fact that since the monitoring stations are tracking the actual satellites all the time, it is possible and is done that this tracking information can be used to produce ephemerides of the actual position of the satellite at the time you were observing it. In other words, given a position on the Earth and given a window of time, it is possible for you to go on the internet and download from these sites I'll give you here the precise ephemeris, the post-computed ephemeris of the moment at which you were observing the satellite. And it's instructive to know why that is so valuable now that we've covered these lessons. It's valuable, of course, because the broadcast ephemeris is not as accurate as the tracking information of the actual satellites you're observing at the time you're observing them. And the reason, of course, is because that the broadcast ephemeris is predictive. It's uploaded with the idea that it's an approximation of where the satellite will be sometime later. Much different to have the tracking information of the satellite at exactly the moment that you were tracking it with your receiver. So here's one, the IGS site, International Geodynamics Service, and then also there is another. In the United States, NOAA, specifically the National Geodetic Survey, also has on their website precise ephemerides that can be used in the same way. Again, this is to do post-processing on GPS observations and much improve the coordinates, if you will, of those control points in the sky, those satellites, with a post-computed ephemeris. These precise ephemerides are usually available 2 to 6 days after the date of the observation. And here again is a website. It's important to note that GPS receivers are installed on other Earth-orbiting satellites and thereby becoming a utility for orbit calculation for those space systems. And so really GPS and these precise ephemerides are very useful in determining positions and getting much more accurate positions using the post-computed ephemerides. Well, now we'll talk more in the next lesson about the user segment, but clearly it's constantly growing. GPS, since it was instituted, has become a utility. It's used in virtually all kinds of vehicles, and it's becoming ubiquitous. The user segment is growing so dramatically it's hard to conceptualize it. And obviously this will continue and be augmented by GNSS, which we'll talk more about in the upcoming lessons. Thank you for spending this time with me.